A long straight wire along the y-axis carries a current of 7.2 amps. In addition to that, there's an external uniform magnetic field represented by B sub 0 of magnitude 1.8 times 10 to negative 6 Tesla. There are 3 points on the xz plane labeled as points A, B, and C, and our task is to find the net magnetic field vector at each of those points. First thing first, let's go ahead and express the external magnetic field vector B sub 0 in unit vector notation. From the picture, we can see that B sub 0 is along the x-axis only. So the unit vector notation will be simply the magnitude of B0 times I hat. Note that in this notation, I have the vector sign here. So this is just the magnitude, and this is the vector B0, the magnitude times I hat, and I have the vector sign. For each point, the net magnetic field vector will be the vector sum of the magnetic field created by the wire at that point, plus B sub 0, the uniform external magnetic field vector. I have expressed that idea in this equation here. This is for point A. The net magnetic field at point A, so that's B sub net at point A, I use superscript A to represent the point A, is equal to the magnetic field created by the wire, so I use B sub W for the magnetic field created by the wire at point A, plus B0. So now we need to figure out the magnetic field vector created at point A due to the wire. The coordinates of point A are given. They're right here. X equals 0, z equals 1.5 meters. So point A is on the z-axis in the positive z direction. And the distance between point A and the wire is equal to its z-coordinate, basically. So this distance right here is 1.5 meters. First, let's determine the magnitude of the magnetic field created by the wire at point A. Now, here's the general formula for magnetic field due to a straight wire of current capital I at a distance r from the wire. It's equal to mu 0 I divided by 2 pi r. We will apply this to each point, starting with point A. In addition, we need to also determine the direction of the magnetic field vector for each point. Now, for that, we need to use the right-hand rule. Imagine pointing your thumb in the direction of the current, which is pointing down in the negative y direction. Your fingers will curl in the clockwise direction as seen from above, like so. So this is clockwise as seen from above. This is the direction of curling of your fingers. If you point your right thumb in the direction of the current, which is pointing down in the negative y direction. At any point, the direction of the magnetic field vector will be tangent to this clockwise rotation. At point A, the magnetic field vector will look like this, parallel to the x-axis in the negative x direction. So this is B due to the wire at point A, pointing in the negative x direction. At point C, again following the clockwise rotation, tangent to that imaginary circle, the magnetic field vector will point in the positive x direction, like this, parallel to the x-axis, pointing in the positive x direction. So this is the direction of B magnetic field due to the wire at point C. On the other hand, at point B, again, imagine the tangent, like so. This one is parallel to the z-axis and it's in the positive z direction. So this is B due to the wire at point B. Now we have determined the direction of each magnetic field vector. For point A, let's combine all this information. Applying the magnetic field magnitude formula, the magnitude of the magnetic field due to the wire will be mu 0 times I, the current in the wire, divided by 2 pi times the distance between point A and the wire, which is 1.5 meters. That's the positive z coordinate, right, of point A. I'm just going to call it z sub A, and it's equal to 1.5 meters. And that is again in the negative x direction. So I need a negative sign here, and I hat plus, so that was the first term, B sub W at point A, plus we need to add the uniform external magnetic field vector B sub 0, like so. So that's it. This is our vector equation. The next step will be to plug in the numerical values and calculate the magnetic field vector at point A numerically. After the numerical calculation, we get 8.4 times 10 to negative 7 Tesla in the positive x direction. Note that the two magnetic field vectors, the one created by the wire and the one that is externally applied, point in opposite directions. B sub 0 is pointing in the positive x direction and BW points in the negative x direction. Because B sub 0 has a greater magnitude, the overall vector sum of the two magnetic field vectors points in the positive x direction. Now let's focus on point C. Point C is on the negative z-axis. Its coordinates are x equals 0, z equals negative 0.65 meters. The same idea applies here. We need to find the vector sum of the two magnetic field vectors, B0 and BW at point C. Now, if you look at the picture, we have already determined that the magnetic field vector created by the wire points in the positive x direction. So B sub 0 and B sub W will be just added up. And to find the magnitude of the magnetic field created by the wire, again, we will apply the same formula, the magnetic field strength due to a straight wire. The only difference will be the distance. Now, the distance between the wire and point C is 0.65 meters. That's the absolute value of the z coordinate of point C. So let's put all that together. Here's the formula for the net magnetic field at point C. The first term represents the magnetic field created by the wire. We have applied the formula mu0I divided by 2 pi, absolute value of z sub c. That's the z coordinate of point C, but we want it to be positive. That's why I have the absolute value sign. And this first term is again positive. This vector is pointing in the positive x direction. And we also have I hat for that reason. We're also adding the external magnetic field vector B sub 0. Now let's plug in the numerical values and calculate. We get 4.0 times 10 to negative 6 Tesla in the positive x direction. Note that the magnitude of the magnetic field at point C is greater than the one at point A for two reasons. One, the magnetic field magnitude due to the wire is stronger at point C because point C is closer to the wire compared to point A. Plus the two magnetic field vectors, the external one and the one due to the wire, point in the same direction at point C. So we add the two together, we add the two magnitudes together. Whereas at point A, the two vectors pointed in opposite directions, so we had to subtract the magnitudes. Finally, let's focus on point B. The idea is the same for point B and the calculations are the same. We have a few slight differences though. First of all, note that point B lies on the x-axis with coordinates x equals 1.5 meters and z equals 0. So then the distance between point B and the wire is equal to the x-coordinate of point B, which is again 1.5 meters. So here I have x sub b for the distance between the wire and the point B. Also note that the magnetic field vector created by the wire at point B points in the positive z direction, hence the use of k hat here as the unit vector. And B0 is still pointing in the positive x direction, So the vector sum of these two vectors has two components, a z component and an x component. So here in the final net vector, net magnetic field vector for point B, I have two separate components. This is the x component coming from B sub 0, and this is the z component coming from B sub W at point B. We can't just combine the two together. We have to keep them separately. This is the unit vector notation for the net magnetic field vector. Now let's find the magnitude and the direction angle of this magnetic field vector at point B. To find the magnitude of our vector, we square each component, add the two together, and take the square root. When we do that, we get 2.0 times 10 to the negative 6 Tesla. So that's the magnitude of the net magnetic field vector at point B. Now let's find the direction angle. Here I have drawn the two components of the magnetic field vector at point B. The z component, which is the magnetic field vector due to the wire, and the x component, that's the external magnetic field B0. We can use the parallelogram method to add the two vectors vectorially. And this is what it looks like. The yellow arrow represents the overall net magnetic field vector at point B. That's the sum of the two components. Now let's find this angle right here. I'm going to call it angle alpha. If we focus on the picture, the x component of our vector, b sub 0 in other words, is the adjacent side for the angle alpha, and the z component, b sub w, is the opposite side. So we could do inverse tan of b sub w divided by b0, or inverse tan of the z component divided by the x component of the magnetic field vector. Here I have set up my calculation. That's the inverse tan of the z component divided by the x component, which is 0.96 divided by 1.8. We get alpha equals 28 degrees. And to be more specific about the direction of alpha, that is the angle pointing from the positive x-axis towards the positive z-axis, the angle right here.